So I hope you can see the shared screen.
Yes, sir.
Okay. So in the previous lectures, we discussed about how LiDAR system operate, the basic principles, and then we talk about the application areas where we use LiDAR based mapping. Okay. So in the discussion of main application areas where we use LiDAR, uh, we have already discussed about the bathymetric applications, and this is different than because in bathymetric application, the LiDAR system uses one additional laser beam, and that is in green band. So this you need to remember. Like as we discussed before, generally the LiDAR system fired the laser beam in an IR band, and considering the eye safety issue. Okay. But for the bathymetric application, we know that the water has reflectance, significant reflectance only within the visible spectrum. So if we use a laser in an IR band, okay, it will completely absorbed and we don't get the return. So this is the reason why for bathymetric application, we use this green laser. Okay. And once you do the bathymetric mapping, so water surface is mapped as well as water bed is mapped. So by using these two information, you can able to estimate the height of the at that particular location, what is the depth of water. And even you can able to map this water bed. So that water bed surface, three-dimensional surface can be generated using the points coordinate which are required. Further, we use the LiDAR-based 3D mapping for glaciers and avalanche. So velocity in case of avalanche can be estimated, and further the risk assessment can be done even if you are doing the scanning on a temporal basis. So at two different epoch, you get a scan point cloud. You can differentiate them and you can estimate how much volume has been already replaced. Okay, so this very detailed quantified analysis can be done. Further, this landslide three-dimensional mapping we do using laser scanning, and that further assist the monitoring of various landslide prone zones. Okay, and we can use the LiDAR for continuous monitoring. Okay, and further it will provide us the information about a prediction of possible slope failure. How we do it, like at a different instance, at a different epoch, what we do, we install a LiDAR system over there and we do the mapping of this entire, let's say this entire area. Okay, so you get a three-dimensional information. See, in this case, we want a three-dimensional information of the surface, ground surface. So what we need to do, if let's say it is a dense vegetation, okay, and we want to estimate the stability of slope. So if it is dense vegetation, then first you need to extract the off-ground point. So ultimately you need to generate a digital elevation model, DEM. So DEM is a representation of bare ground. Okay. So how you get DEM? First, you need to remove all the on-ground object. Like in this case, the all on-ground objects are trees. Okay. So in a LiDAR point cloud data, you need to remove the trees first. Then using the ground coordinate information, you need to generate DEM. Okay. So you do it at a particular epoch. Then at later time, okay, again you need to do the 3D mapping using LiDAR system. Okay, same process you need to adopt, and you need to generate a, let's say, DEM at time t2, and that is a advanced time, and DEM at time t1. If you differentiate these two 3D surfaces, then there you will get information about at what location you can notice the change. Okay, and on the basis of that change, that will indicate you the volume of material, a volume of soil that has been removed from there. Okay, and where it is logged. So on that basis you can able to estimate the change in the surface. Okay, and if that is measured, then this slope stability can be estimated. And why LiDAR is a kind of tool that we prefer over here for the landslide mapping, because in LiDAR, that already we have seen that it can penetrate through the canopy and it goes to the ground, unlike the other image acquisition techniques, okay, where we get only the pixels information of tree cover. Okay? That can't compute ground information under the trees. Okay, so LiDAR is a preferred choice over here due to its capability to penetrate the tree canopies and goes to the it go to the ground. Okay, and that ground information, geometrical information, is also estimated. This is the reason why once you remove the on-ground objects like trees, still you have ground points, and using those ground points, digital elevation model can be generated. The meaning of DEM is like in LiDAR point cloud data, you have information about what is the location where the point lies. Let's say if we select a point P1, let's say somewhere here, I select a point P1. Okay, so corresponding to this point P1, okay, we have its planimetric location, okay, where it is in 2D, so that is XY. And along with the XY, we have information about what is depth, okay? What is the Z value, what is the height of the where it is actually in the 3D space. Okay, so this is and further, if we select some adjacent point P2 over here, again for P2 we have its location in two-dimensional plane, okay, in a plane, and its height, that is Z2. Okay, to generate DEM, what we do, DEM is a kind of information of this elevation. So we interpolate the surface using the Z values at various XY locations. Fine. So ultimately, digital elevation model is a representation of ground terrain. Okay, how it varies with respect to height. So that information we generate in TEM. Now further, this LiDAR technology is useful for the forest mapping, where we can generate DEM. Then after that, we can extract the trees, like as I discussed before. If you see the point cloud data, if I plot over here the cross section, let's say, so there could be the houses. There could be a tree. Okay. So as I discussed before, for generation of DEM, you need to perform ground filtering. Let's say these are the points whose coordinates are computing while laser scanning. Okay. So in ground filtering, what you need to do, uh, using certain set of algorithms, only you need to identify these points. So these points are identified, and you need to remove all the on-ground points, like points belong to the trees over here, as well as points belong to the building. Okay. So in ground filtering, ultimately what we do, we separate input point cloud data. That is, all these points coordinates are known. Okay. Let's say in a particular reference coordinate system, if I define over here, and generally it is defined as WGS84. It's a global coordinates. In WGS84, we calculate coordinate of all these points using LiDAR based operation. So while the ground filtering, you need to separate out the ground points as well as non-ground points. Okay. So ground points and non-ground points, they are separated in ground filtering. As you see over here, when you separate the non-ground points, some data gap will be there. Like if you see this location, we don't have any ground points over here because this area is obstructed by the building roof. In case of trees, due to the advantage, like laser beam can penetrate through the canopy, we'll get enough points under the canopy from the ground. So there will not be the problem. But when you generate DEM, so DEM is a kind of elevation surface, you can say, where by using the existing this ground points information, you can interpolate the missing area. So just see, this is the DEM surface, it is generated. So this is a mathematical surface that we generate using the various points coordinate information, like, and these are the ground points which are generated after the ground filtering. Okay. So this is a distribution model, and this this is one part. The second part, once you separate a non-ground points, okay, so there are various objects of interest in non-ground points. If I talk the forestry, so in case of forestry, the object of interest is trees. Okay. So the trees are the object of interest, and in forest mapping and forest inventory, generally we estimate the information related to the trees, like the computation of biomass volumes. Okay. Various morphological parameters of the trees, like if I say, so the morphological parameters of the trees will be like height of the tree, then we calculate diameter, dBH, then 3. Biomass. Then you can also calculate the inclination, the tree axis inclination from vertical. Okay, so there are various other parameters which can be accurately estimated using the LiDAR point cloud data, because we have a detailed geometrical information of the trees. Okay, so to calculate these parameters, what you need to do first, you need to segment out the trees from the rest of the non-tree object. Obviously, when we talk about the forest, so forest in majority we have a trees only. But when we talk about in urban context, so we have urban trees and other urban objects like buildings are there. Okay, in majority, the road network are there, some other objects are there. So there is a requirement to develop algorithm to understand the algorithm. There are already many algorithms for trees identification from LiDAR point cloud data. So this part we will discuss in data post processing. Once you understand the entire technology, like how the accurate and dense point cloud data we acquire. So once you have understanding of data acquisition system, okay, then after that we will discuss in the last 2 units how the various objects of interest are extracted from the point cloud data and what are the existing algorithms, what are the future scopes, okay, and where the research in this area is moving. Okay. Now further, this LiDAR we use for the urban applications, where again, as in the previous slide, I talk about various objects of interest can be extracted from the LiDAR data. If we talk the in urban context, buildings informations are also extracted. Building informations are also captured. Like if you see in this case, this is the photograph. Once the laser scanning is performed, then after this is the surface model. Okay. So when you have, let's say, if by using aerial scanning and terrestrial scanning, if you do if you perform the survey, or if you perform the 3D mapping, so what is there from different facades of the building? Let's say I'm just putting the dot over here, the coordinates from the rooftop, various points coordinate from side, every corner will get a point coordinate. Okay, so using those coordinate information, and that those coordinates will be in a fixed coordinate system. Those points coordinates are calculated in the fixed coordinate system, and we are considering WGS84. Okay, so what you can do, you can generate surfaces, you can generate a 3D model, okay, using this point cloud. But before that, you need to identify these buildings in the point cloud data from rest of the objects. Okay, so building extraction has to be performed first. Once you have a building point cloud data, then you can generate a building information model, BIM. Okay, so 3D modeling can be done. Okay, and further this building information model of an entire city can be generated. Okay. Now, the LiDAR can be further used for the change detection, like in case of any calamities, in case of any structural damage. Okay, after any type of disaster, let's say in earthquake. Okay, so if you have a 3D model before that event, and after the event you perform a 3D mapping, you will get different information, and you generate a 3D model for both the cases. Then you can quantify what is the structural damage that happened over there. Okay, so actual volume and complete structural damage in detail can be estimated. Okay, let's say in a case some buildings are collapsed. Okay, and after that, when you do the laser scanning, you will get the actual 3D actual information. And before the event, you have the information. Then by subtracting these two surfaces, these two models, you will get information about like how much damage, structural damage to the building has already happened. Now further in urban applications, we have various facilities like drainage. We have a utility network planning to lay down various utilities, utility-based facilities. Okay. First, you need to generate a 3D model of entire city, as you see over here. So once this LiDAR can assist to generate detailed and accurate 3D model of entire city, where you have a structural detail of buildings, trees, road network, and all other objects. So using this entire model, you can plan for the various utility network. Okay. And you can optimize your planning to lay down these utilities on the actual site. Then further, in case of any, so this emergency route planning can be done. Like you know the information about the road network, you know the what is the width of the network, whether it's a single lane, it is dual lane. Okay, all information is there with you. So this emergency route planning can also be done when you have a detail, three-dimensional detail of the city. And there are various GIS applications. Okay, like you can identify the roadside trees, you can identify roadside buildings, roadside this utility poles, street lights. So these are the various object of interest. Even you'll see further this transmission lines and power lines. Okay, you can see that in our scenario, like if you see in Allahabad or in your city, so at many places these power lines are encroached with the trees. You can notice that tree branches are encroaching to the power lines, and that is one of the main cause for the power flow while summer. Okay. Once you do the 3D mapping, you have information about what is a power line route. Okay, power line, this catenary detail is there that will be captured. Dense trees canopy and tree location is captured. So that kind of obstruction, okay, that kind of encroachment can be identified very easily. Okay, and further the required corrections can be done. So this for the cellular network further, like Cellular network is different. Like here we talk about a reach up a signal from the tower. Like sometime you can feel that at a particular place you have very weak signal, very weak network for your mobile phone. Okay. So that once we have a, because this signal strength entirely depends on the how dense the city is and what is the location of this telephone tower. Okay. So that sound propagation modeling as well as this that is a different part, and this signal propagation modeling can be done. Okay. So nowadays in telecommunication industry there is a fixed algorithm to install the tower so that that can provide a maximum coverage. Like if this telephone cellular tower is installed somewhere with the assembly of various antenna, how that location is optimized so that it can provide a maximum coverage. So there will be the here this LiDAR based 3D point cloud model of the city will assist to finalize the actual optimal location where that telephone tower should be installed so that it can cover the maximum area. So there will be the requirement of building outline, ground covers, and various other abstractions. So that information we already collect to the LiDAR point cloud data. So there will be the analysis based on lineup site, some view set analysis, etc. Now further we have use LiDAR based 3D mapping for the mining applications. Okay. So for the mining application, we can estimate the actual volume of the ore that is extracted while the mining work. Subsidence monitoring can be done and the planning for mining operations. Like let's say if this is the excavation site, how you can estimate the actual volume of the material, actual volume of ore uh, uh, that has extracted. What you can do just before the extraction or excavation process, do the laser scanning, generate a 3D surface. Then again after the extraction, do the scanning and generate a 3D surface. Just subtract these two surfaces, you will get actual volume that is extracted from the site. Okay. Then subsidence monitoring. If there is a sudden depression at the ground, that can be further monitored. Okay, by analyzing the change in the surface at at a very at many instances. Okay, so the time series data we collect to analyze the change in surfaces, so that will provide the information that help us to monitor the sustenance, and it is very common in the mining site. Then further planning mining operation that can be done. Now the corridor mapping, whether it is rail or road. Nowadays, the LiDAR, this specifically for rail and road, the mobile LiDAR system has been adopted as a remote sensing technique. It is a preferred choice for the roadway related construction and maintenance. So once you have a map data of a road network, that will assist for planning and maintenance purposes. Okay. And for like here I talk about rail and road corridor. Similarly, the gas and oil pipelines corridor, power line corridor, everywhere by using LiDAR, very detailed geometrical information is available. Okay, and that help for the various application. As I discussed before, for the power line corridor, we can identify the encroachment of trees to the power lines, the catenary which pass through between two poles. That catenary information, that the wires which are going from one pole to the next pole, the point cloud from those wires are collected. Like let's say if this is an electric pole and we have a next electric pole. So by using laser scanning, we get information about the coordinate of various points from the power lines. It is there, and let's say somewhere it's a tree, and these tree branches are encroaching to the power line, so that hazardous situation can be assessed. Okay, and based on this, the required corrections can be done. Like there is a requirement to trim the tree branches so that it will be isolated from these catenaries, okay, which connects one pole to the next pole. So once you have a power line corridor mapping data, this can be done. Even in this context only, if you see, you frequently notice between two electric poles, after a certain period, there is a sagging effect in the wire. The wire sags, and what happens? The gap between these two wires is decreased. So while in summer season, if there is a heavy winds, what happens? These two just connect, and that is also one of the reason for the power failure. So once you have a three-dimensional information of these wires, these gap analysis can also be done so that the required corrections can be applied over here. Okay. So similarly, like we can perform the various geometrical analysis. Like in power line corridor, we talk about two cases. The first one, the encroachment of tree branches to the power line, it can be identified. And similarly, the various catenaries which passes through from one pole to next pole, their gap can also three-dimensional gap between that can also be identified. Okay, and the required maintenance has to be performed on that basis. So this is high voltage transmission line, and this high voltage transmission line, just see in this figure, you can notice these points are representing the catenaries which are connected between two poles, between two transmission towers. Okay, so while the transmission line based mapping and further the monitoring, the tree location, tower location, these catenary models, vegetation critical distance analysis, like what should be the optimal distance that has to be maintained between the wire and tree canopy. Then it further, once we collect these information, this will help us to carrying out repair and planning work. Okay, so we have discussed about few of the applications where the LiDAR system based 3D mapping assist, okay, to solve the various challenges. Now we start our discussion with general understanding of LiDAR system, in particular the terrestrial laser scanning. So we'll see how it operates, what are the internal modules in this terrestrial laser scanner, okay, and what is the mechanism through which the laser beams are fired, and the point cloud data from the terrain are required, okay. So as you see in this case, this is a terrestrial laser scanner, and it is 3D laser scan. 3D laser scanner means it compute the range from transmitter aperture and the angle alpha from vertical axis, z axis, and this beta from either x or y axis. So there are angle encoders. Angle encoders calculate two angles, and this there is a receiver, transmitter, and counter circuit. Using these components, the range is calculated. And just see below in this figure, this is a color coded point cloud, three-dimensional point cloud data that is acquired through the terrestrial laser scanning. It's not a photograph. If you zoom it at the certain level, you can see the gap between the points, but they retain the actual color. So the data is collected so dense, like you can see all the points are very closely packed. So they looks like a continuous surface. Okay, here you can see the internal architecture of 3D laser scanner. Okay, so the first component is that is laser range finder. So this laser range finder has receiver and transmitter. Okay. So transmitter means the electronic unit that fires the laser beam, and the receiver is the electronic unit that sends the return corresponding to the fired laser beam. And similarly, we also have a counter circuit. So we'll see internal architecture of laser range finder later on. So this counter circuit measures the total time of travel. So through the laser range finder, laser beam emanates like over here. This passes through the lens, like let's say somewhere here. Internally, we have a laser range finder unit. It fires the laser beam, and this is the mirror. As you see over here, this is the mirror, and it is positioned over here in inclined way, and it continuously rotates 360 degree in vertical plane. As you see over here, so this is same. So this mirror is represented over here, and it rotates. So there is a vertical rotation. It rotates in a vertical plane. And what happens once it rotates, this normal, while rotation, the normal from this surface changes. Okay. So due to change in normal, it provides a different direction to the laser beam, and the direction will be in a vertical line. Okay. So in the vertical plane, along a particular line, once it rotates 360 degree, the laser beams are hitting. Okay, like let's say if if this rotating mirror is at this location, so laser beam hit this particular point. Now let's say it further rotates and there is change. Okay. Now what happened if there is a change? In the previous case, this was the normal. So it is mirror, the laser beam is hitting, it is reflected back. So Snell's law apply over here in the previous case. Now what happens when it rotates to the new location? Let's say this is the new location. Then normal will be this. Normal will change. Now it will held to the next point. Okay. So in this way, with a rotation in a vertical direction, this rotating mirror divert a laser beam along the vertical line. If I say over here, in the ground, it's not a vertical line, it's a particular reference direction, you can say. So there will be two directions will be defined and they will be perpendicular to each other. So the way it hits the ground, it all depends on what is the orientation architecture of this orientation architecture of this LiDAR instrument determine. Okay. Okay, fine. Now, if you initialize this LiDAR system, and this with respect to the rotation, again and again on the same line, the laser beams are fired, and the same points coordinate are calculated again and again. But our aim is to cover the entire the area in the surrounding of this laser scanner unit. What should be done? Again, you need to provide a horizontal rotation. Okay. And now just see, now this entire system, this entire instrument rotates in a horizontal direction. So that now the second line, adjacent line will be covered, then third, fourth. Okay. And in its field of view, if in a vertical, it is rotating 360 degree, and in horizontal as well, it is rotating 360 degree. So entire area in the surrounding of this LiDAR instrument is scanned, and the coverage depends on the what is the maximum range. How long from like so this coverage around the this LiDAR system, this TLS, depends on the maximum range covered by this scanner. And in your laboratory, we have been discussing about how this instrument operate. So it's Faro Focus 3D X330. So Faro is the make and X330 is a model. So Faro is a company that manufacture this TLS. And the model version that we have is X330. It means 330 meter is the maximum range that can be covered. Okay, so this is the basic operation that talks about how when you initialize a LiDAR system, a TLS over here, okay, and after the initialization, it acquires the points coordinate in its surrounding up to the maximum range that is given for that particular instrument. Okay. Now we'll see the working of laser rangefinder. Okay. What are the internal components of laser rangefinder? Okay. So there is a laser source. Okay. That laser source generate, let's say, the laser beam. I'm considering here a pulse laser. Okay. and there is a mirror. It passes through it. When this laser pulse emanates the laser transmitter aperture, a trigger signal is generated. Fine. And we call it the receptor restart. So this trigger signal triggers the counter. There is a timer circuit. It is counter circuit. Okay. So this receptor signal is triggered through the timer circuit, and it starts the counting. This laser beam goes, hit the target, then return back. Now it is sensed by the receiver unit. This is optics that collect the laser energy. Okay. And after collection of laser energy, that is, there is internally the receiver circuit. Once it is received at the receiver, at the optics of the receiver, again a receptor stop signal is generated, and it further triggers the timer circuit to stop the counting. So in this way, using this electronic component, the total time of travel that is taken by a laser beam from the transmitter to the receiver end is recorded. Okay. And as you see in figure C, it is a representation of hemispherical surface within which the laser scanning is, within which whatever the objects which are present, if they are hit by the laser beam, their coordinates are computed. Okay. And as I discussed in the previous case, when the vertical rotation, so in the vertical rotation, when the mirror rotates, this line is covered. And when the scanner rotates on its own, entire scanner assembly rotates, then it shifts to another line. Okay. So we have a series of terrain profiles, and that we get by the horizontal as well as vertical rotation that we provide to the this laser scanner unit. Okay. Do you have any doubt? If you have any query, please discuss.